welcome back to the course on blockchain. So, in the last discussion, we have looked into the consensus mechanism in blockchain, consensus, the general distributed consensus architecture. So, in this particular talk, we will look into that how consensus is achieved in Bitcoin based permissionless blockchain environment. So, here is the consensus algorithm in Bitcoin. So, the objective of the consensus algorithm is in Bitcoin is to add a new block to the existing blockchain. Now, there can be multiple miners in the Bitcoin network, and individual miners can propose their new blocks based on the transaction that they have heard of. So, one miner can heard the transactions 15, 16, 18 and 19, whereas another miner can heard the transactions 15, 16 and 17. So, it is interesting to note as I have also mentioned in the last lecture that it is not necessary that every miner will propose a new block or better to say every miner will propose a same block. So, it is all like that whatever transactions the miner has heard of till now, or better to say that the time that the last block has been added in the blockchain, they can include all those transactions in the new block, provided that the total size of the block does not exceed certain threshold. So, in this particular example, we have 3 miners. So, these individual 3 miners have the 3 individual blocks which have been proposed by them, and the objective here is to decide that which particular block need to be added to the existing blockchain. So, the consensus objective is that which block do we add next out of the 3 blocks proposed by the miner. Now, the challenge here is that the miner do not know each other, because it is a open network, it is a permissionless network. So, anyone can participate in the network as a miner, and they can collect the transactions coming from the clients and they can propose a new block. So, under these certain scenarios, how will you ensure that the miners will come to a consensus? So, let us look into one possible solution which is more closer to the traditional distributed consensus algorithms, where every miner, whenever they are proposing some new blocks, they will broadcast the information in the network, and after broadcasting the information to the network, they will wait for a certain amount of time and see that whether they are receiving any other blocks from other miners, and based on that they will apply a choice function to select one of the blocks. But there is a problem in this particular mechanism. So, what is the problem? The problem here is that whenever we are saying that a miner will wait for certain duration, that is technically infeasible under this particular environment. Why? Because first of all, the miners do not know each other. Because the miners do not know, they do not know that how many other miners are there in the network who are going to propose new blocks. And the second one is that the internet is inherently asynchronous. Asynchronous in the sense like whenever a miner will propose a block, there can be arbitrarily delay in transmitting those new blocks. So, in this particular environment, having a consensus based on a broadcasting algorithm by applying traditional distributed system mechanism may not be feasible. So, if you remember the impossibility theorem, where we have mentioned that coming to a consensus is impossible in a purely asynchronous distributed network in the presence of even a single failure. So, in this particular architecture, even if there is an miner which is an malicious miner, even in the presence of a single malicious miner, other miners may not be able to collect all the blocks which are coming from the legitimate miners, and having a consensus by applying this kind of traditional distributed algorithm based on broadcasting or based on message passing is infeasible in this scenario. So, let us see that what we can do. So, we have 2 different observations here. The first observation is interesting, that in case of a blockchain environment, any valid block can be accepted. So, a valid block means a block with all valid transactions. So, we can accept any of the proposed block if it is valid, and even if the block is proposed by a only single one miner. So, it is not necessary that the block need to be proposed by multiple miners together. Even if it is coming from a single miner and it is a valid block, we can accept that block and we can connect that block to the existing blockchain. So, that was our first observation, and our second observation is that the entire protocol can run in rounds. Run in rounds means like once a valid block has been accepted or say the system has reached to the consensus, from that point a round starts, the miner starts getting the transactions, and then they can find out that which are the transactions which are not already committed in the blockchain, and based on that they can propose the new block. So, if you look into this particular example, in this example the last block in the blockchain, it has transaction 11, 12, 13 and 14. So, all the miners, once this particular block has been committed in the blockchain, the miners they can find out that well, transaction 11, 12, 13 and 14 has already been committed. So, we do not need to include those transactions again in a new block. So, they can propose a new block by excluding the transactions which has already committed in the blockchain. So, that way once a commitment has been done, that means a block is added to a particular blockchain, the miners can try to figure out which are the next transactions that need to be added to the blockchain, and they can propose the new block based on that. So, based on these two observations, we can design a solution in this way, where every miner they independently tries to solve a challenge. So, the challenge is provided by the network. So, they will independently try to solve a challenge, and the block is accepted for the miner who can prove first that the challenge has been solved. So, this particular keyword proof first is important here, because this keyword says that every individual miners they are trying to solve a solution imposed by the network, and the miner who is able to solve the problem first, they add the solution of the problem to the existing block and add that block to the blockchain. So, this particular algorithm is known as proof of work. The term proof comes from the fact that the miner he has been able to, the miner who is proposing the solution, he was able to prove that he has found out a solution of the problem. So, that is the solution architecture, that when the miner finds out that there is a solution, he proposed the block to the other miner saying that well, I have already received the solution. So, he has already received the solution, and other miners they stop finding out the solution for that challenge and start finding new blocks in the from the transactions that which are coming from the clients. Now, one interesting point to note that this particular communication can work asynchronously. So, whenever you are advertising the solution to the other miners in the network, the miners can work for mining the previous block during that time. Say I am a miner, I am trying to find out the solution for a given challenge, and whenever I will find out that well, a new block has been added in the blockchain, during that time if I find out that well, that particular block has certain set of transactions which are also part of my block. So, there is a overlapping of transactions between the block that I am trying to prove or I am trying to mine and the newly added block in the blockchain. If that is the scenario, then I can just stop the mining at that point, accept the most updated blockchain, and then start finding out blocks with new transactions which are coming from the clients. So, once the solution has been obtained, so the block has been added to the existing blockchain. So, this block with transaction 15, 16, 18 and 19 has been added to the blockchain. Now, the interesting fact that whenever this particular information, this updated blockchain is propagated to all the miners in the network, so all the miners can see. So, the other miners they were at that time they were also trying to mine the blocks where these transactions 18 and 19 were there. So, if you look into the earlier slide, so this miner was also trying to mine a block where transaction 15, 16, 17 was there, the second miner was trying to mine a block where transaction 15, 16, 17, 18 was there. Now, this new block has been added to the blockchain and they can find out that well, in the newly added block transactions this 18 and 19, 15, 16, 18 and 19 they are there, but transaction 17 has not been included in the block. Now, in the next round every miner can include transaction 17 and at the same time along with transaction 17 the other transactions that they have had within that time duration. So, those transactions can be added and they can start mining those specific blocks. So, the same process repeats in rounds and they can try to find out that what can be the solution for that particular challenge. So, what should be the challenge? So, to generate the challenge, Bitcoin relies on a mechanism called proof of work. So, what is a proof of work? A proof of work is an economic measure to deter service abuses by requiring some work from the service requester. Usually, it is processing time of a computer. Say, if you are requesting for a service, you have to show to the service provider that you have spent significant interest on the service that you are requesting for. So, I will give you an example that how this kind of proof of work based system can help you to prevent junk emails or spam emails. That is an interesting idea, but the broad idea of this proof of work is that every service requester must spend some time on the service that he or she is asking for before actually requesting for the service. So, that way it shows you from the economic perspective that the service requester has some interest on the service. So, if the service is provided to that service requester will genuinely accept that service and it will not use it maliciously. So, this idea is actually an old idea which came from Dork and Naur in 1992 from an interesting paper published in a crypto conference to combat the junk emails. So, in that particular paper the idea that they had shared that you have to do some work to send a valid email. Now, the attacker this way they will be discouraged to send junk email because in that case they have to do the same work of the same complexity over the junk emails that will not prove beneficial for them. So, this kind of proof of work based system they should have certain features. So, one important feature is the asymmetry, that means the work must be moderately hard, but feasible. So, you should try to solve moderately hard, but feasible work to the service requester side, whereas at the service provider side the work must be easy to check or must be easy to validate. So, that way the service requesters they will get discouraged to forge the work. So, because they have to spend some significant amount of time to complete that particular work, they will be discouraged to submit any kind of spam or junk work to the system. But service providers on the other hand, they can easily check the validity of the work because of the asymmetry nature that the work is easier to validate for the service provider, but it is hard, but not infeasible for the service requester. So, let us look into that how cryptographic hash can work as a good indicator for proof of work. So, while discussing about different type of cryptographic hash functions, we have looked into the puzzle friendliness property of cryptographic hash function. So, the puzzle friendliness property says that given x and y, you need to find out k such that y is equal to the hash of x and k appended with each other. So, if x and y are known, in that case it is very difficult to find out this certain k. You have to, the best algorithm to find out this kind of k is to apply a certain kind of brute force mechanism or some kind of random search over the possible values. So, this particular work it is difficult to find, but it is easier to validate. So, once you have found out such k, it is easier to find out it is easier to validate whether the hash value of x appended k becomes equal to y or not. Now, this concept was used in Hashcash. So, this Hashcash work was proposed by Adam Back in 2002 which was a proof of work mechanism that can be added with an email as a goodwill token. So, it is like that the hashcash can be only generated, or the legitimate email senders will be interested to generate a hashcash, whereas the spam email generators, they will be discouraged to generate a hashcash. So, let us look into the details of this hashcash mechanism and how it works. Now, this hashcash proof of work is an textual encoding, or you can think of it as a hashcash stamp, which is included in an email header. So, this hashcash is a proof that the sender has expended a modest amount of CPU time to calculate the stamp before sending that email. Now, if the sender has spent a modest amount of time to generate the hashcash before sending the email, it is unlikely that the sender is a spammer, because the spammer will be interested to send repeated emails one after another by some auto generated script. So, if they have to wait for certain amount of time for sending every emails, the spammer will not be beneficial out of that. But on the other hand, the email receiver, they can verify the hashcash stamp very easily by applying certain hash function. But any change in the header also requires a change in the hashcash, because you are generating the hashcash from the header. So, if you want to modify certain field inside the email header, you have to regenerate the hashcash, which is for which the brute force is the only way to find a new hashcash. So, that way the attacker will also be discouraged to tamper the email header. So, here is an example of a hashcash. So, the hashcash which is included in an email header, it looks like that. You have a hashcash field. After the hashcash field, you have certain individual fields. So, the first field 1, it talks about the version number. So, we are using hashcash version 1. The 20 is certain number of bits, or we can say that it is the number of 0 bits that need to be there in the hash code. So, this 20 says that you need to generate a hash function where the first 20 bits of the hash function would be 0. So, that is the challenge which is posed to the email sender. Now, the email sender has to find out a hash value where the first 20 bits are 0. Then the timestamp value, date, here it was generated on 1st April 2018. So, it is that year month date format 18401. Then certain resource, here I have put my email ID. Then a random number, a string of random characters. The string of random character is included in the hashcash, and what is the importance of this string of random character, that we will see later on. And then a counter value. So, this counter value is working like a nonce. So, the email sender, for them, this all the fields like the version, number of 0 bits, the date time stamp, the resource field, the string of random characters, all these fields are fixed. The only field the email sender can change is that counter field. So, the email sender need to check with different counter value, by providing different counter value, that for which counter value it can find out the expected hash value, where the objective is to have a 20 number of zeros at the prefix. So, in the sender side, the hashcash is constructed in this way. So, you first construct the header. So, the construct the header, you have individual fields. After putting individual fields in the header, then the sender initializes the counter value to a random number. So, once the sender initializes the counter value to a random number, then the sender compute in a traditional hashcash. We use 160 bit SHA-1 algorithm. So, by applying 160 bit SHA-1 algorithm, you try to find out a hash value where the first 20 bit of the hash is all zeros. If you can find out a hash value where the first 20 bit of the hash is all 0, then that particular hash is accepted. Otherwise, you try with a different counter, you change the counter value and check with a different counter value and find out that whether the resultant hash produces that required 20 bit at the beginning or not. Now, at the recipient side, the recipient checks certain parameters, the date should be within 2 days as per the hashcash version 1. So, if someone is changing the date, if some email spammer or some attacker is making a change in the date version, he need to again recompute the hash cache. The email address, it checks that well the email address in the hash cache it exactly matches with the sender email address. So, that means the sender has generated that particular hash cache value and a random string. So, this random string should not be used repeatedly within a certain duration. So, it prevents the replay attack. So, the replay attack is something like this, where the attacker has stored a previous hash cache, the attacker has cached the previous hash cache, and by caching the previous hash cache with every junk email, he or she is sending that previous hash cache. So, this random string is utilized to prevent those kind of replay attack, where every time whenever you are sending a new email, you have to change that random string. So, if you change the random string, you have to generate a new hash cache value, and that way you have to spend certain time to generate the corresponding hash cache. Now, once you have checked all the fields, next time is to validate the hash cache. Validating the hash cache is pretty easy. You take the entire string, find out the 160-bit SHA-1 hash function out of that string, and if you can find out that well the first 20 bits are 0, all zeros, that means that was your earlier objective, that you can find out by looking at the string that the first 20 bits should be 0. So, if the first 20 bits are all zeros, then you accept that particular email, otherwise you discard that email. Well, some analysis of hash cache proof of work. So, because we are utilizing 160-bit SHA-1 hash function, so you can have 2 to the power 160 possible hash values. Now, what we want, that if you want 20 bits at the beginning, that means you can have 2 to the power 140 possible hash values, which satisfy the criteria, where the first 20 bits are zeros and remaining 140 bits can be either 0 or 1. So, the chance of randomly selecting a header with 20 leading 0 bits at the prefix, that probability is 1 out of 2 to the power 20. So, that means if you can try with 2 to the power 20 different hash function with a high probability, you can get a hash value. So, that way the expected number of rehash the sender has to do is 2 to the power 20, which takes a certain amount of time. In today's computer, it takes in the order of few seconds to compute the hash cache, but on the other hand, validating the hash cache at the receiver side is very fast. The receiver requires around 2 microseconds to validate the hash cache. Okay. So, now there is an interesting exercise for you. For this hash cache, you can go to the website hashcache.org. So, here is the hashcache.org website. In the hashcache.org website, you can find out the hash cache source in different languages. So, under source directory, the library, the hash cache source is available in generic C, DLL, Java, Python, even in Perl, C#, Shell script. In different languages it is available. So, I will encourage you to download this source. The source is very simple and you can just do a direct execution of that. So, executing that particular script, I will suggest you to follow these exercises. First, download with the source and try with different number of 0-bit targets. So, you can increase the number of targeted 0 bits at the hash prefix, say from 20 to some 2020 at a step of 100, and observe the time to compute the hash cache. So, the output that you will see, you will find out that as you increase the number of leading 0 bits in the prefix, the time will actually increase exponentially. So, if you increase the challenge, if you increase the complexity of the challenge, it will take more time to find out the corresponding hash cache. So, that way you can determine that at what difficulty you can put the challenge to the email sender. If you want that well, the email version should have some 100 leading 0 bits. That means you are actually trying to design a system where the sender have to do a lot of work to find out that Hashcash, but they will be you will be able to guarantee strong security of that system, and you will be able to prevent the junk email significantly. Then on the recipient side, you use this SHA-1 sum script, which is a standard tool available in most Linux computers, to compute the SHA-1 checksum of the obtained Hashcash value from the above experiment. By doing that SHA-1 sum, SHA-1 sum will return you the 160-bit SHA-1 checksum. Then you can look into that checksum field, and you can find out that well whatever number of bits you have asked for, or whatever number of 0 bits you have asked for in the prefix, whether that many number of 0 bits are there in the prefix or not. And also you can find out that how much time it is taking for the recipient to validate the hash just by applying this SHA-1 sum tool on the obtained Hashcash value. So this would be an interesting exercise for you. In the next lecture we will discuss about Bitcoin proof of work, which is based on this Hashcash based system. In today's lecture we will stop at this point. So in the next lecture we will see you, and we will look into the Bitcoin proof of work mechanism in further details, which is based on the Hashcash based system. See you again. Thank you.